Welcome to the next lecture on information theory. So as in previous class we had defined relative entropy between two distributions, suppose P and Q, okay, and on alphabet set, suppose S is equal to S0 to Sk minus 1, okay. So it was defined as d of P, this is a notation, k equal to 0 to k minus 1, pk log ratio of two distributions pk and qk. Now we proved one important property, that relative entropy is always non-negative. Today we will use this important property to prove another property of an entropy. Suppose, in fact, here is one small theorem, that the entropy of a source is upper bounded by logarithm of the size of this set. How many elements are there? Log of k. Okay, so we'll try to prove it. It is now very simple. So what should we do? So first of all, we take two distributions. So one is the P, okay. So of course P is, what is P? It is probability that any symbol, suppose if we take pk, any symbol sk, the random variable s takes some value sk, and qk is also the probability that random variable takes some value sk. But these are, you can think of two different people who are guessing these probabilities. Whereas pk we think of a true probability, guess, and qk is a guess which may or may not be correct. That is its interpretation. But otherwise, mathematically, you can just take pk, qk are two probabilities, and d of pq is the differential entropy between the two. Sorry. Now if we choose, if we put qk equal to 1 over capital K for all k, this is also called uniform uniform distribution. That is, qk, we are taking a distribution wherein it can take any value with equal probability. Random variable s can take any value with equal probability. Then differential entropy between the two, since it is defined like this, pk by qk, right? Now what is this qk? So it is pk log to the base 2, so it will be k times pk, right? Because you will put this as 1 by k, it means k times pk, and that will become log of ab is equal to log of a plus log of b, right? So what is first quantity? So what if I write here minus and minus outside? And it is here log k right. Now what is this quantity? This is minus here, and this is entropy of source. And what is summation of pk? Since pk is a valid probability mass function, its sum should be equal to 1. So this is the value of differential entropy between any distribution p and uniform distribution qk is equal to 1 by k. And we know that it should be always greater than or equal to 0. So which means minus h of s plus log 2k should be greater than or equal to 0, and we get the desired result. Now let's little bit interpret it, what it means. It says that suppose you have a source S, random source, which can take on any of these values, right? And you can define any probability distribution over the source. So now corresponding to any probability distribution, this source will have some entropy. See, I repeat, entropy is function of probabilities only. It doesn't depend upon the values which this source takes. What are the actual values of S0? Sk doesn't enter into the entropy. But what is the probability with which you pick up S0? What is the probability with which you pick up Sk minus 1? That is the only factor which enters here. Now, out of all probability distributions, which probability distribution will give us the maximum entropy? So if you look at this, suppose you have a coin toss, head and tail, head map to 0, tail map to 1. Okay, or let me retain the notation. Let's write this as S. Okay, so this is your S0 and this is your S1. S0 is equal to 0 as 1. Now if probability S equal to 0 is 0.1 and probability S equal to 1 is 0.9, that is probability of head is 0.1 and probability of tail is 0.9. This is one scenario. Other scenario is probability of S is probability of head is 0.5 and probability of tail is also 0.5. Now I ask you, and you should yourself think, in which scenario you will be most confused or most uncertain if you throw a coin for a toss? Definitely in this scenario 1, since probability of tail is more, so you will be always biased towards tail. So if you throw the coin and if you bet with any person that what will it will be, so if you know the probability of tail is 9, so it is safe and you will be less uncertain about this, and you will most of the time bet on that it will be tail. Whereas here, since both the events have equal probability, uniform probability, so you are most confused here. There is more uncertainty here, that is the thing. See, now in terms of information content, if you throw this type of coin, which is biased coin, where probability of head is 0.1 and tail is 0.9, if someone throws a coin and tells you that I got tail, you will not gain much information because you are already biased. You are knowing that tail has high probability. Whereas here, if someone tells you the result, I have got head or tail, you will feel that you got more information because you were more uncertain because they had equal chances. So that is in one way the interpretation of this result, that for any source entropy, the upper bound in case of discrete sources is log of 2 to the log of k to the base 2, and this entropy log of k to the base 2 is achieved when we take probability distribution as uniform distribution. Suppose in case of coin tossing, you have this Q0 is equal to 1 by 2 and Q1 is equal to 1 by 2, because in case of coin tossing this K is equal to 2. Okay, now there are some examples in the book, not all, but example 1 at least you should study properly and try to solve it. Now that is it for entropy. And now so in the book, if you see, after entropy they study source coding. In fact, that is the main one can say that one of the motivation for introducing entropy was source coding and compression, but I will not go into that direction. Okay, I want to take you in the direction of communication systems. So sorry, we will be studying now the channel modeling. Okay, so we will be studying now discrete memoryless channel. See here again, the way it will be introduced, you will see it that you don't really need till now even you don't need really a rigorous understanding of communication systems. Okay, so till entropy we were worried about a single random source. Okay, which was generating random symbols. Right, so we were mostly concerned about random generation. Now what if we transmit this source or something called a noisy channel? Okay, now what is noisy channel? Let's give an example. Suppose you are only transmitting binary symbols. Okay, 0 and 1. So here is your source. This is source of this 0 and 1, and here is something called a noisy channel. Now what can this noisy channel do? So this is the receiver. Okay, and this is something you can call transmitter. So this noisy channel, what can it do at most? It can do two things. Two effects can be there. One is very simple. This channel changes 0 to 1 or 1 to 0. This is the one thing. Or other thing is channel may erase the bit. So at the receiver you will see nothing. Channel is such a bad channel, it erases the bit. So this effect 1 is more prominent and more it appeals our common sense that whatever, suppose here is your mobile at transmitter side, here is your mobile at receiver side. We are not concerned about the circuits, how modulation is done, what is actual channel. No. Suppose you transmitted some symbol and that contains zeros and ones. Suppose you transmit 1. Receiver may receive either 1 or 0. That is the end result. How this 1 got converted to 0? There can be several reasons. The wireless channel in between, there is so much distraction. There is a noise inside the receiver. Whatever be the reason. So in information theory, we will never open these boxes. Rather, we will do something called statistical modeling. Okay, so that is the reason I took up this a part of the concept beforehand, so that even if you are from computer science background, you don't need to open up these boxes. What is transmitter, what is receiver? We will do statistical modeling, and in particular there is a particular statistical model for communication channels, that's called discrete memoryless channel. So what we have here, so we have input. Okay, input is what is being transmitted by the channel, so that is represented by x, a random variable x, and output will be represented by y. What is y? Y is a noisy version of x. Okay, suppose this mobile transmits these bits, we call them x, and this mobile receives, we call it y. Okay, so whenever channel, whenever transmitter transmits something and puts it on the channel, receiver will receive correspondingly y, we call it y. Okay, and x can take values from a set. Again, it's just like an alphabet set, or I can say alphabet set script x. Okay, and y can take values from script y. So let me clear this confusion here itself. For example, in most common cases, this x can be, for a binary case, 0 1, as well as y can be 0 1. It means a random source at transmitter can either generate 0 or 1, and at the receiver also you may receive either 0 or 1. But what will be this channel? What is the role of channel? It may flip 0 to 1 or 1 to 0, or may transmit 0 and 1 as it is. Okay, so first of all, now the reasoning that why it is called discrete. So this channel is called discrete for obvious reasons, because both input and output alphabet sets, see, these are called alphabet sets, x and y. X and y have finite size, right? See, another example of suppose if you club up 2 bits at a time, 0 0 0 1 1 0 1 1. This is another example of alphabet set. So this can be called as S0, S1, S2, S3, right? So this is the reason for calling it discrete. And then comes the term memoryless. What does memoryless mean? It means that when current output symbol depend only on the current input symbol and not on previous symbols. Okay, suppose if I am transmitting 0 1 0 1 1, right? This is x, and correspondingly I receive 0 0 1 1 0. So you can see that there is an error at this position, there is an error at this position, and there is an error at this position. I will be teaching you error control codes also at the end, how to correct these errors. Okay, but right now there are errors, so this is your y. But what will be the output at, suppose you transmit this bit at time t is equal to 0, correspondingly you receive suppose this bit. So the result at t is equal to 0, then at t is equal to 1 you transmit this bit, and at t is equal to 1 you receive this bit. At t is equal to 1, what you receive at the receiver does not depend upon what was transmitted in the previous time. Okay, it doesn't depend upon what was previously transmitted, but in some cases it may depend. But when it doesn't depend, it's called memoryless channel. Okay, and here is very simple. Now, how to give a statistical interpretation to it? So first of all, we will define input alpha bit for a general channel. Let's say that it takes values, suppose x0, x1, xj minus 1. So it can take any j values, and output alpha bit y0, y1, yk minus 1. It can take any k values. Okay, so as an example, if we think of this 0 1, here j is equal to 2, right? And x0 is 0, x1 is 1, and y, if y is also 0 1, then k is also equal to 2, y0 equal to 0, y1 equal to 1. Okay, then we can have even more symbols, just like combinations of 0 0 0 1 1 0 1. Now here is a way to represent it. So it can take any of these values, x0 through xj minus 1. Okay, and the random variable which denotes that it can take any of these values will be denoted by x. Now here is a channel, and at the receiver we receive y, which can take any of these values, which is the alphabet set y. Now this x can be chosen with some probability. See, these appear to be random sources. When you will see random bits coming out of a source, you can perceive it as some random process, random variables coming out, right? So we have some probability mass function defined for this x, and there will be a probability mass function corresponding to y also. In fact, one of the genius strike by Shannon, who proposed the information theory, was to represent channel by probabilities. Now how can we represent channel statistically? What is channel doing? Channel is taking the input alpha bit and sometimes is changing 0 to 1, sometimes changing 1 to 0, or sometimes it does not changing. How will we quantify it? So it is quantified by conditional probability that you will get some yk at the output given that xj was transmitted. Okay, suppose you have input x and it takes any sample value, particular value small x. Okay, and with this conditional probability, receiver will receive output y with some sample value y. Okay, so this channel is called a discrete memoryless channel. We will call it DMC now onwards. And by the way, when we say that suppose x is x0 to xj minus 1, then this j, which is the size of this set, is also called cardinality of set x. Okay, this is the term, which actually means number of elements in alphabet set. Similarly, what will be the cardinality of y? Cardinality of y will be k. And these probabilities are called transition probabilities, which characterize the channel. Transition probabilities. P of yk given xj, which is probability y is equal to yk, x is equal to xj for all j and k. Okay, let me give a very simple example before I will generalize the things. Okay. This is example 5. This is your homework also. Homework in the sense you have to study it and try to solve yourself, but I will just give example. Okay, it's called a binary symmetric channel. It is very simple channel, but at the same time one of the best model for most of the communication system channels. So what is it? It is here 0 or 1. So your alphabet size is here, it is 0, 1, your j is 2. Okay, so what can channel do? Channel may transmit 0 as it is, so receiver also receives 0. Okay, or it may flip the 0 to 1, so receiver may receive 1, or channel has to transmit 1, it may transmit this 1 as it is, so receiver receives 1, or it may flip the bit and receiver receives 0. Now these are all random. So this is your input, this is your output. So these are all random events. So suppose if 0 is flipped to 1 with probability p and 1 is flipped to 0 with probability p, then 0 is transmitted as it is with probability 1 minus p and 1 is transmitted with probability 1 minus p. In fact, to write it properly, we can write probability y is equal to 1 given x is equal to 0. Okay, that is p. Probability y is equal to 0 given x is equal to 1, that is also p. Probability y equals 0 given x equals 0, that is 1 minus p. Probability y equal to 1 given x equal to 1, that is also 1 minus p. Okay, these are the transition probabilities. Now we can arrange it in matrix form. So we can write first probability y is equal to 0 given x equal to 0. Probability y is equal to zero given x equal to 1. Probability y equal to 1 given x equal to 0. Probability y equal to 1 given x equal to 1. We can form a matrix and this will be equal to here 1 minus p, p, p and 1 minus p, and I can represent it with some capital P. Okay, so this is called transition probability matrix. If you see, this transition probability matrix completely determines the channel. What will be the effect of channel? Okay, if someone tells you, suppose that transition probability matrix is 0.3, 0.7, 0.7, 0.3. See, we are saying it is binary symmetric channel because the probability with which 0 changes to 1 p is same as the probability with which 1 changes to 0. It can be different also, but we are assuming it to be same. So even this matrix is symmetric. Okay, so P transpose is same as P, symmetric matrix. So what does this mean? It means that 0 is transmitted as it is with probability 0.3, 0 is changed to 1 with probability 0.7, 1 is changed to 0 with probability 0.7, and 1 is transmitted as it is with probability 0.3. Okay, so definitely, since any conditional probability of yk given xj, right, that should be less than equal to 1 and non-negative, right? And given any symbol transmitted xj, the probability of receiving yk, if you sum over all k's, that should equal to 1, right, for fixed j. Just look like here. So for x is equal to 0, in this case, for x equal to 0, probability y is equal to 0, suppose it is 0.3. For x equal to 0, probability y is equal to 0 is 0.7. So 0.3 plus 0.7 should be 1. Right? Now, for general channel, discrete memoryless channel with alphabet x j minus 1, y is equal to y0, k minus 1. Here is the transition probability matrix. Okay, this is just generalization of what we have written for 2 cross 2. So it is J cross K matrix, and it is called channel matrix also. So it's also called stochastic matrix. The reason for calling it stochastic matrix is this one, that probability yk given xj for all k is 1. So this is the reason for calling it stochastic, if this is satisfied. Okay, and as I told that the input, the source bits are also coming up from a random source. So we define p of xj as probability x is equal to xj for j equal to 0 to j minus 1, right? And we will have probability of yk equal to probability of y is equal to yk. Okay, but how will we characterize probability of yk? It is the what you receive at the receiver. So it should be characterized in terms of input probabilities and channel transition probabilities, right? Now for that we note one thing, that probability yk we can get it from the joint probability xk and yk. This is a joint PMF. How we get marginal out of joint? We should sum it over all, sorry, we have to write here xi or xj, so we should sum it over all j. Okay, see, this is how we get marginal from the joint, which I have told you in the last lecture also. You sum over the other random variable. Suppose you are given the joint random distribution, you sum it over x, you will get the marginal probability of y. Right? Now, how can we write this in terms of known quantities? So how do we write joint? So I will repeat, probability of yk given xj, conditional probability, is equal to probability of xj yk divided by probability of xj. Hence probability of xj yk is equal to probability of yk given xj probability of xj, right? So we can write it here, probability of yk given xj probability of xj. Nice. Now this is for j is equal to 0 to j minus 1, k is equal to 0 to k minus 1. Now you see we are given, this will be given to us. In fact, these probabilities will be in our control. In this sense, you are generating the source bits, so you can control it. When should be 0 transmitted, when should be 1 transmitted. So in some sense you have some control over it. Okay, you can encode the data properly such that zeros and ones come with particular probabilities. Okay, and the other thing which is not in your control but you can get knowledge of it, that is the conditional probability of the channel transition probabilities. Right? Now given these two, if you sum it over all the possible values of x, then you get probability of getting any particular output symbol. Okay, and these are called the input probabilities, they are called prior probabilities also. Okay, so we are all set. We have developed a notion of binary symmetric channel, and in next class we are now all set to define mutual information. But before that, we will be defining conditional entropy, okay, which I have written here also, but it will be covered in next lecture. So I will just give a hint of it, what it is. So what we will be doing next time is, first, what is the entropy of y at the output given x was transmitted. This is called conditional entropy. Okay, this I will define in next class, and then we are all set to define a very important quantity that is called mutual information in next lecture. Thanks.